Hello and welcome to AI4. Our next session will be led by Phoebe Liu. She is a senior data scientist at Appen. Please join me in welcoming Phoebe to the virtual stage.
Thank you, Patricia. So today I'm going to be, so I'll share my screen first. Hi, everybody. So my name is Phoebe. I'm a senior data scientist at Appen. So today I'm going to be talking about training conversational agents on noisy data. The topic I want to highlight today will be three things. So how do we do data collection and annotation for conversation agents? How do we design dialogues for conversation agents? Specifically, I'm going to highlight the example of social robots. And how do we use data-driven techniques such as learning by imitation to train social robots? I would also like to highlight some of the work related to social robot work done at my previous research institute, ATR, back in Japan. So with that, I would like to first talk about the data collection and annotation strategies for conversation agents. So many of our customers are making conversation AI, and it's actually quite difficult to do so. This is an example I actually pulled out from chatbot.fail. And as you can see, there are multiple instances where the chatbot fails to respond to the customers. And this in turn causes frustrations and disengaging the customers. So to build a dialogue system, this is sort of the typical process for building conversation AI. Some aspects are complicated, but we don't have to worry about it. But this is the basic process. So at first, we have speech recognition system, which will output the ASR results. Sometimes, depending on the language, domain, accent, or whether there's background noise, the ASR results can be quite noisy. Next, we have the NLU, which takes up the understanding of the data based on grammar, the context in which it was said, and decide on an intent and entities. Then the dialogue management system handles what state the conversation should move to turn by intent. And this can be either handcrafted or probabilistic. The natural language generation components generates narrative that describes, summarize, or explain input structure data in a human-like manner. And depending on whether it's a voice AI, there will be a last component, TTS, which synthesizes speech to audio for the users. So to collect data to train the NLU components, we found a lot of customers, this is a typical workflow. First, they will have to define an intent. So for example, if somebody wants to build a chatbot to assist customers for grocery shopping, they will define a list of intents. Then for each intent, then we can collect a set of paraphrase utterances related to that specific intent. Then the third step is the entity extraction. So for each token in the utterances, we have a key and a value. So in this example, the key will be the type, the cuisine type, and the value is vegetarians. So I would like to highlight some of the challenges when we're designing dialogue. So first, we know that we often see in our platform, the customers try to figure out the intent for the NLU model in that domain. And based on that domain, collect a variation of paraphrase utterances that maps to the intent. But I think this is actually a chicken and egg problem. Without really knowing how real conversation go, it is hard to define and collect these human intents by hand. Second, it is actually quite hard to model real world conversation flow. So even if you collect conversation scripts and want to use it to design dialogue, it's not always a one-to-one mapping where we're responding to the immediate previous utterance. So much of what we say depends on the context, the conversation histories, or things that are actually not modeled in the scripts, for example, the environment. So as you can see, some of the conversation flow can get really complicated really fast. And actually, the third challenge I would like to highlight is the noise. We often find that data collection can be noisy and costly. So if you're collecting spoken dialogue, as I said, the ASR results can depend on variations of factors. And here is an example of what I mean. This is a data set we collected of 5,000 utterances in a semi-noisy environment where two people are having conversation with each other about buying a camera. As you can see, there's a lot of ASR noise. For example, synthesize or weight is recognized wrong. And because of the natural variations and unscripted conversation, we also see people are using what we call disfluency or filler words like, oh, I see, I think, yeah. So this all can add to noise in the data. So with this particular data set, we found out that 47% of the data was noisy. To address some of the problem with utterance quality, at Appen, we actually developed various machine learning assisted validator to guide the worker how to annotate. For example, in utterance collection tasks, we can use machine learning to do the first check whether workers are submitting semantic relevant or coherent utterances or not. Then we have the second step, which is a data verification audit process. So for example, when a new utterance is collected, and then goes to another job where 3 crowd workers judge the validity of the utterances, whether they adhere to the data collection instructions. So only after all the utterances have been verified, then we'll reward the worker in the data collection phase a bonus. And so this incentivizes the worker to try to do a good job. So based on the study, we act by combining these two strategies with the machine learning assisted validated and the data verification workflow, we were actually able to improve the utterance quality by 30% while maintaining the same annotation cost. So next, I'm going to talk about, once we collected all these data and annotate them, how do we actually go about to design dialogues? Specifically, as I said, we'll use social robots as examples. So what are social robots? They are not devices that interact with peers. They need to communicate using speech and gesture, and they provide useful service. As you see, they can be deployed in a number of environments, in supermarket, museum, shopping mall, or train stations. And maybe a lot of people are familiar with similar systems in the real world, things like autonomous vehicles, having to deal with things like navigation, path planning, safety, and avoiding obstacles and peoples. And also voice assistant that handles hard questions like question answering or responding to comment. So the question is, where do social robots fit? The answer is actually both. They're related to both. Instead of avoiding objects and people, the robots need to approach and engage people. Instead of following in clearly defined traffic rule, you have to follow fuzzy implicit social rule of our society. And like voice assistant, it also has to do conversation like question answering, but it should have a personality because there is embodiment in a robot. Aside, it should handle complex multi-turn conversation or multimodal and mixed initiative interactions. So as I said before, with dialogues, there's two approaches. One is a more heuristic, handcrafted interaction. And this is actually one thing we try to do with our robot is, with this, we can actually really control the character of the robot exactly the way we want. So to do this, we actually develop a flowchart visual programming language. So programmer can program behavior in the robots and combine logics like speech, gesture, and emotion to enable the robot to talk or shake hands. And one of the examples I would like to show is Erica. She's a highly human-like android we have developed back in Japan. So over the course of several months, we iteratively add contents and behaviors to enable her to have a characters and to sort of talk with visitors to our lab. And here is an example of her interaction.
Hello there, may I ask your name?
My name is Ignacio.
Ignacio, is that right?
Yes.
It's nice to meet you, Ignacio. So, what country are you from?
I'm from Canada.
Wow, Canada's quite far away. It's pretty cold there, eh? Anyway, as you probably already know, I'm from Japan, much like many other advanced androids and robots. My name is Erica. Would you like to hear a little about me?
Yeah, go for it.
I'm an android developed at ATR to be capable of human-like speech and interactions. I was built in Tokyo, but I've spent most of my time here at ATR, so I consider this my home. So Ignacio, what do you do for a living?
I'm a student.
Oh? You're a student? Make sure to study hard. As for me, I don't exactly have a job, but I am designed to be capable of human-like speech and interactions. I do know a few robot jokes. Would you like to hear one?
Yes, please.
What is a robot's favorite kind of music?
What kind?
Heavy metal. Haha. How about another one? A robot walks into a bar, orders a drink, and lays down some cash. The bartender says, "Hey, we don't serve robots here." Then the robot says, "Oh, but someday you will." Ha.
So as you can see, Erica is highly capable of very human-like conversation, and this is all designed through our by manually scripting interaction flow. But with Erica, we also found out that while we can design her behavior, we also need a way to continuously put new knowledge in her so she can learn about the world. So the idea is that some of our knowledge is implicit. So it's actually hard to program the social knowledge into the robot because we don't really exactly know why we do the things we do. So it's actually difficult for people to articulate exactly what they say in different situations. So with that, we went and conducted another study with a different experiment in the ancient capital of Japan, Nara. So with this, we used another robot called RoboV. He acted as a Nara Tourist Information Center, and we hired volunteer guides, tour guide, to ask them to create some offline content for the robot in order to bootstrap the dialogue system for this robot. So this is what we expect the human operator to input, which will be a little bit quite human-like natural conversation. But then what we found out is that the content was not conversational at all. It sounded like a tourism brochure. So this is the idea of teleoperation. So the idea is when the teleoperator is controlling the robot, the system can capture any new knowledge or update existing robot behavior during real-time interaction and use this to update the robot's knowledge base. And by capturing this behavior in real time, when the operator is fully immersive in the situation, we're able to get very natural behavior for the robot. Here, I would like to sort of show a video of the demonstration of this experiment.
奈良の玄関口 JR 奈良駅で今日観光客を出迎えたのは
こんにちは。僕の名前はロボビーです。
観光ガイドロボットロボビー。京都の研究機関が最先端技術を駆使して作ったというこのロボット、人と会話ができるというが、まずはお手並みを拝見。
今日は大仏様に会いに来ました。
大仏様は東大寺の大仏殿という建物にいらっしゃいます。大仏様は奈良時代約1260年前に聖武天皇によって作られました。
このロボットの最大の売りは遠隔操作ができるということ。ロボットには想定される質問の答えがあらかじめ登録されていて、出歩くことが困難になった高齢のボランティアが自宅からでも簡単に操作できる仕組みになっている。
So with the study, you can see that the robot can continuously learn and generate natural behaviors through teleoperations. But with this technique, even though we found out that it's better than just using offline content creation, but it's still quite expensive to run because it requires to deploy a robot. And it's not scalable. The other thing is that the operator can be quite slow and error prone. So it can't provide, one of the things the robot can provide bad service to visitors, but if the visitor has to wait 2 minutes for the robot to respond, that's going to provide a bad experience. It's also hard through this method to control for multimodal behavior. So with that, we actually conducted another study, which we set out to collect in situ data collection from real human interaction and use this to train the robot to generate autonomous behavior. So with that, I would like to move on to the next topic. So the idea is if we can crowdsource interactions from human, we can use these to generate robot behavior. And the key challenge is that we want to do this all without data annotation. So we set up a data collection in a camera shop where the participants role play as customers or a shopkeeper, where they spoke and act naturally without any script. The interaction is multimodal, so it consists of speech, locomotion, and proxemic. We also had a human position tracking system that reports people's movement in terms of X and Y every second. The user also carry an Android phone for speech recognition. One thing we found is that natural conversation is very noisy, as I was saying before. With this data set, we only found 53% of correct and noise-free utterances. Another thing we found is that there are natural variations that arise from person to person. So even though they all represent the same action. So for example, people can use different phrases to say things that are semantically similar. So even though there are natural human variation, at its core, there are actually some common repeatable behavior pattern people usually do. So we can actually extract this data into meaningful representation of typical behavior element. For speech, we use a standard NLP technique that can represent the ASR result into an utterance vector. Then once we have these vectors, we can then cluster them, and then extract typical utterances for that cluster. For motion, the raw data is reported as X and Y, but raw sensor data occupy a high dimensional space. So we can also use abstraction to simplify the learning problem. And what we actually want to know is the location and where they're moving to. To do so, we can cluster the motion data as well, and we can extract the typical location and moving trajectories in terms of where they stop or where their motion origin and target is. For proxemic, they can be easily described in many different situations. So for example, we know what face-to-face look like, whether they're in a museum or a shop. So we identify waiting, present product, and face-to-face. Once we found the typical behavior, we can then discretize the interaction into customer and shopkeeper action pair. So whenever a customer speaks or moves to a new target, this action is discretized. Once we discretize and represent the customer or shopkeeper action as joint vector, we can actually use this to train a machine learning model. And here is actually the result. We have over 135 trials with around 1,200 robot behavior. Here's the results. Because of our abstraction technique, the robot behaved 85% correct, whereas the ASR only reported 77% correct. So this actually means the robot outperforms the ASR results and can handle noisy data. And so I would like to sort of show you a video demonstrating what I mean.
Hi, is there anything I can help you with today?
Yes, this camera. How's the battery life?
Long battery life of 9 hours.
Oh, I see. And the weight?
This camera is 150 grams and can fit in your pocket.
Oh, wow, that's very convenient. Thank you.
Okay.
How about this one? How's the storage memory?
Yes, it can store 10000 photos.
How much is it?
This is $400.
Okay. What colors does it come in?
The intense rain red and brown colors.
Okay. Oh, actually. What's the optimal zoom on this camera?
X optical zoom.
Okay, thank you.
No problem.
So as you can see here, the robot was able to respond to the woman's actions even when there is some speech recognition error, and it can also respond to the woman's movement and where she's moving to in the space. So with that, I would like to conclude my presentation. And some of the key takeaway is that with data collection and annotation, it's always good to use in pseudo data collection approach to capture natural conversation whenever possible. When you're designing your data collection workflow in a platform like Appen, make sure to have multiple steps and process, like a data verification process to ensure high quality data. When you're dealing with noises, you can also use machine learning assisted validator to reject noisy data from the onset in data collection platform, like what we found have a lot of success with our customers, and use abstraction or machine learning technique to reduce noise in your training, when you're training dialogue. So with that, I would like to share some of the references I mentioned in the paper. And with that, I would like to thank everybody for attending. And if anybody has any question, I'm happy to answer. Thank you.
Thank you so much, Phoebe. That was an incredible presentation. And now I kind of want to go shopping with these robots. That sounds like fun to me. Thank you again for your insight, and a huge virtual round of applause. Woo! All right. If you're headed to your next session, you can go ahead and check out the program page to find where you're going next. Also, take some time to connect with your peers through our networking channels. All right, we'll see you around. Thank you.